Okay, let's look at an example on chapter 8. Let's say we have a a mass flow rate flowing through a pipe, and let's say the pipe is at 100 degrees Celsius, and our fluid flowing is water. It's flowing at 0.25 kgs per second, and at the inlet, the temperature of water is 15 degrees Celsius, and at the outlet, it leaves at 57 degrees Celsius. And let's say the diameter of this pipe is 0.05 meters and the length is 6 meters. Okay, now our intention for this problem is to find uh, the Q, the heat rate through convection, and to find the heat transfer coefficient. And we'll look three variations of the same problem in this particular video. So the first thing we need to do is we need to find the properties, the thermal properties of the fluid, and for that we need a reference temperature. So uh, as we know that we'll use the mean temperature of the fluid uh, to find the properties. So we'll take an average of the temperature at inlet and outlet. And why is that? If you just say that you'll take the temperature of the inlet, you know that the fluid is going to be at a higher temperature than that, and the mean temperature will be somewhere between the inlet and the outlet. So that's why we use the average temperature to calculate the thermal properties. So our average temperature is 36 degrees Celsius, and the thermal properties at 36 degrees Celsius from table 8.6 are the Cp is 4178 joule per kg Kelvin, your Prandtl number is 4.62, and your thermal conductivity is 0.628 watt per meter Kelvin. This has to be meter Kelvin. Then the next thing is that we need to characterize our flow. So to characterize our flow, we need to know what our Reynolds number is. And to find our Reynolds number, we should know what our mean velocity is. So to calculate our mean velocity, we've seen that it's related to the mass flow rate. So the mass flow rate can be written as density times the mean velocity times the cross-sectional area of the pipe, and your U mean will be mass flow rate divided by the cross-sectional area, which comes out to be 0.127 meters per second. And then the definition of Reynolds number will have this mean velocity, your viscosity, and the characteristic length will be the diameter of the pipe. So entering the values, we have density as 1000, we have velocity as 0.127, the mean velocity is 0.127 meters per second, diameter is 0.05 meters, and the viscosity is 695 into 10 to the power minus 6. This gives us a Reynolds number of 9137. So the critical Reynolds number for internal flow is 2300. So because our Reynolds number is greater than this, our flow is turbulent. So our next step should be to find a relationship of Nusselt number for this particular scenario, which will help us find a heat transfer coefficient. So equation 8.6 from your textbook can be used in this scenario. So this is the equation that we have. Nusselt number is uh, given as 0.023 times Reynolds number to the power 4 by 5 and Prandtl number to the power n. And the book gives us two values of n. One is if if your fluid is heating, and the other is if your fluid is cooling. But in our scenario, we have our fluid heating as it moves along the pipe. So the value of n in that case is 0.4. And on substituting the value of Reynolds number that we just found here, and the Prandtl number which we got from the table, and substituting the value of n, we get our Nusselt number as 62.54. And we know the relationship for Nusselt number is Nusselt number equals to h d divided by kf, where k here is the thermal conductivity of the fluid. So on substituting these values, we get our heat transfer coefficient as 785.6 watt per meter square. Now we have our heat transfer coefficient, but there are two ways of finding or of calculating Q. So one easy and common way used in such problems, because you know what the mass flow rate is, you know what the inlet and outlet temperatures are, and because you know the surface temperature, you can simply calculate your Q, and this will be Q convection obviously, as m dot Cp into Tmo minus Tmi. So using that relation, your Q will be 438,969, 43,869 watts. Okay. Now let's look at another method. In this method, we can let's say you're not given some values, or you're not given a mass flow rate, and you're asked to find out the Q or something, and you're just given a heat transfer coefficient, and you know the temperatures of the surface temperatures and the inlet temperatures. So this is another method that you may use based on the problem. So we'll just apply this method to the same problem and see how our solution is and how different it is. So we can say that our Q is equal to the average heat transfer coefficient that we calculated times the surface area of the pipe times the logarithmic mean temperature difference. And the formula for the logarithmic mean temperature difference is delta TO, that's the temperature difference at inlet minus temperature difference at outlet, divided by the natural log of the two temperature differences is at outlet and inlet. So substituting the values, we have delta TO as TS minus TMO. So usually you use this value when you have a bunch of different heat transfer modes, or you have different thermal resistances. That's when you use the LMTD temperature, but we'll apply it in this case and see what we get. So our delta TI is TS minus TMI, which is 85 degrees Celsius. And we have already calculated our average heat transfer coefficient. We know the dimensions of the pipe, and we know the temperature differences. And on substituting that, we get our Q as 45,633.85 watt, which is different from the Q that we got in our previous method, which was 43,869. So if you are given an inlet outlet temperature, and if you have a purely internal flow where the surface temperature is known, you use this method because it's easier. But if the question says that you have to calculate the heat transfer coefficient and calculate the heat rate, you can use this method as well. So moving on, let's look at another variation of this problem. So let's say you have the same pipe, same flow through the pipe, and now the pipe has a particular thickness. So you have internal diameter as 0.05 meters, but now the external diameter is 0.06 meters. So the thickness of your pipe is um, um, 0.05 meters basically. And let's say you don't know the surface temperature of the pipe, but what's given is that you're given an external temperature. So you have you have air outside which is at 35 degrees Celsius and has a heat transfer coefficient of 10 watt per meter square. And we also know the thermal conductivity of the pipe, which is 100 watt per meter Kelvin. So what we do is that we'll calculate the total thermal resistance, which will be a combination of convective resistance inside, the thermal resistance due to conduction of the pipe. We assume that there is no contact resistance, so we ignore that. And the third is convective resistance outside the pipe. So our total resistances will be the addition of these three resistances because they are in series. And we've already solved such problems in chapter 3. So this will be equal to delta T by Q. Now I can write my Q as the mean temperature of the fluid inside minus the temperature of the surrounding divided by the total resistance. And if I rearrange this, I can write the total resistance inverse times the Tm minus T infinity, and I define the total resistance, the inverse of total resistance, as U times A, where U is the overall heat transfer coefficient. And usually U and A are written together, and we'll see why. So now we need to calculate this total resistance. So R1 divided by U1 A1. So you can either say that you can either have your overall heat transfer coefficient for your outside pipe or your inside pipe. If you're taking for the outside pipe, you can say it's U2 A2. If you're taking for the inside pipe, you can say it's U1 A1. And your resistances will be 1 upon H1 A1 plus resistance due to thickness or due to conduction plus resistance due to convection outside. And on substituting the values of H, the dimensions of the pipe, so your area will be surface area, which will be pi d into L, plus resistance due to conduction, and plus the convection of air is 10 times pi times diameter 0.06 times the same length of 6. So this gives us a total resistance of 0.0898, and if you take an inverse of that, you'll get U1 A1, which is equal to 11.13 watt per Kelvin. Now you can calculate the heat rate between the liquid inside the pipe and the surrounding air, which is at 35 degrees Celsius, by calculating the delta T, the logarithmic mean temperature. Now what I've done here is that I've assumed that the logarithmic mean temperature is 61. I've taken the logarithmic mean temperature that we've calculated in the previous method 2 and calculated the heat transfer rate, which is wrong because in the previous in method 2 we had considered the in the definition of logarithmic mean temperature we had considered surface temperatures instead of T infinity. So here we'll have to so here our delta T Lm will be T infinity minus Tmo divided by, oh, just wait. Sorry about that. So this will be delta T O minus delta Ti divided by ln of delta To divided by delta Ti. But the definition of delta To will now be T infinity minus Ti, To, and the definition of delta Ti will be T infinity minus Ti. So your delta TLm will be different from this value here, and your solution will not be 685.97, but I want you to calculate these values and substitute in this equation here and find the value of